our problem is compute the definite integral from 0 to 1 of x squared e to the 3x with respect to x. Normally, we would compute this using a double integration by parts. Then we would have to take care with the use of parentheses and the distribution of minus signs. For here, I want to focus on exam strategy. So our method's not going to use integration by parts. It's going to be a direct memorization trick. Now, the trick has two parts. So for the first part, whenever we take the antiderivative of, say, x to the n e to the 3x, what we do is the terms that we're going to use, we'll start with x to the n e to the 3x. Then we're going to put in a term for each lower power of x. So we'll have one for x to the n minus 1, x to the n minus 2, and so on, till we're down to the term e to the 3x. Now, what's missing are going to be the coefficients in front of each term. The way we find those is by using our check for antiderivatives. So, recall, if we have the antiderivative of little f with respect to x equal to capital F plus the constant of integration c, that's the same as saying the derivative of capital F is just little f. So let's see how we use that. Now, in our case, we have antiderivative of x squared e to the 3x with respect to x. So I'll use x squared e to the 3x, and then all lower powers of x. So I'll have x e to the 3x and e to the 3x. We'll call that capital F, our antiderivative. So if we take the derivative of capital F, I expect to get back what's in the integrand. So that's x squared e to the 3x. Now, we can compute the derivative of capital F. It's just going to be the product rule and the chain rule. And that takes a little bit of work, but we can do it. So we're going to get this big mess here. And we set it equal to x squared e to the 3x. Now, when we pull out the a, b, and c, we're just going to match up like powers of x times e to the 3x. So, for x squared e to the 3x, we go through. On the left side, we'll have 3a. On the right side, the coefficient here is going to be a 1. So I have 3a equals 1, or a is equal to 1/3. For x e to the 3x, okay, on this side we go through, so we'll have a 2a. Then, okay, we keep going, we'll get a 3b here. On this side, there's no term, so the coefficient is going to be 0. So we have 2a plus 3b equals 0. I know what a is, so we get b equals minus 2/9. Finally, we just look for e to the 3x on both sides. So what are we going to have here? We'll have a b and a 3c. On the other side, there's no term, so we give it a 0. Since we know a and b, that gives us c equal to 2/27. And now we just put those in, and we have our antiderivative, and we can apply the first fundamental theorem of calculus. We apply the first fundamental theorem of calculus. So we take our antiderivative capital F, I evaluate at the upper and lower limits of integration, take the difference. If we put a 1 in here, I could factor out an e cubed. Then we just have 1/3 minus 2/9 plus 2/27. If we put a 0 in, these terms go to 0, and we're left with 2/27. So our final answer is 5/27 e cubed minus 2/27. Now, for here we can check. So if I put this in a calculator, I'll get roughly 3.645. If I go to my computer, calculate the Riemann sum, so that's just going to be an approximation using rectangles. If I let the base of each rectangle be equal to 0.001, my approximation is 3.655, and that's pretty close to what we're getting here. So I believe my answer. For another check, we can just work out the antiderivative the long way using a double integration by parts. So here's the setup, and I'll just leave it to you to pause and work your way through it. But you'll see you get the same antiderivative when you work it out the long way.